Hello guys and welcome back to CS with Mr. G. This is the second lesson of Unit 4, which is all about software. And in the first lesson, we simply looked at different types of software, including application software, system software, and the roles and responsibilities of the operating system. In today's lesson, we've got quite a few learning objectives to get through, and we also have some very technical keywords and what could be some new terminology for those who aren't that familiar with different programming languages. But as you can see, first and foremost, we have to explain the difference between a high-level and a low-level language, including the pros and cons of each type. Secondly, we're going to look at this term assembly language. So we need to know what assembly language is and how it looks. And then we also need to understand how assembly language is what we call translated into machine code. So machine code is quite easy to understand, but there's a process of translation between these two terms, and this is something else we'll go through. We are also going to look at the difference between a compiler and an interpreter, which are two methods of translating high-level languages into a low-level language or machine code. And then finally, we will weigh up the advantages and disadvantages of a compiler and an interpreter and go over a brief summary of all of our new keywords for today's lesson. So a lot of new keywords today, a lot of technical jargon that I will try my best to break down and make this quite tricky topic as easy as possible to understand as I can. So first and foremost, if we just cast our minds back to Unit 1, where we discovered that everything in the computer is represented as binary. Binary being zeros and ones, and this includes all forms of multimedia, text, images, sound, graphics, videos. Everything we discussed in Unit 1, we discovered that everything is represented as binary. So with that in mind, we also need to understand how programming languages are also converted into binary numbers. If we first take high-level languages, and for those who are familiar with some of the languages that you can see here, Python, Java, or C++, these are what we consider high-level languages as they are easy to read for human beings. They tend to use words that we can understand, such as print or input, but they are considered high-level because we can understand them as human beings. So these are just 3 examples. There are thousands of languages in today's world, especially when it comes to programming languages. But any language that you've probably used in 2025 would be considered a high-level language. If we take the complete opposite and go down to a low-level language, this is what we consider machine code, which goes back to what we said earlier, which is zeros and ones or binary. So machine code is what the computer understands. It's not anything that we can read or write. It's simply the zeros and ones that the computer needs in order to process our lines of code and execute the instructions that we write. So machine code, or the binary numbers, are what we consider the low level. They are the lowest level language, and they would literally look like a series of zeros and ones that you can see here. So high level, humans, just think of the H in high and think of the H in humans. Low level is the lowest of levels, which is the binary numbers, the ons and offs in electricity inside the computer. Now again, we just need to cast our minds back to Unit 3. And in Unit 3, we looked at instruction sets, especially when it came to different CPUs and the instructions that were assigned to different CPUs and how they might differ across different brands or different manufacturers. We said that all these different devices and these different brands or manufacturers would have their own set of instructions assigned to each one. Now, how this ties into today's lesson is that we need to show knowledge of the opcode and operand, which we've also previously mentioned in that lesson. We can now label this as a low-level language and show knowledge of what it looks like and what it consists of. But don't worry, you would never be expected to write in this language. You just need to be able to identify it and recognize it as a low-level language or machine code. And just as a reminder from that lesson in Unit 3, the opcode is the instruction that's being processed, for example, adding or subtracting a number, loading a number, or even storing a number. And the operand is the value that's being operated on, which could be the address of the value or the actual value itself. And as you can see, they are just binary numbers that the computer can read and understand. We would never be expected to read or understand any of this. Now, as machine code is considered the lowest language of all languages, as this is how a computer operates in the form of electricity, one of the very first languages that was implemented in computer science is what we call assembly language, which you can see on the right here. An assembly language was developed as a direct translation from machine code, which you can see on the left. Now, what's important for us in terms of assembly language is that assembly code uses what we call mnemonics in order to represent the opcode, which we've just previously looked at. For example, the machine code on the left here, the binary numbers that you can see, This can be directly translated as add into the accumulator with the numerical value of 16. That's what each one of these directly translates as. Now, in the early days of programming, this is how lines of code would have been written by programmers, which then would have been translated into machine code in order for the computer to run. And if we just look at some examples of how assembly language looks, you can see here, you've got words like mov, which represents move. You've got add, which we've already discussed. And you've got these letters here, which refer to registers within the CPU. And you've also got the numerical values here. Now, each one of these can be directly translated into machine code so that the computer can understand the binary equivalent. Now, what's important for us is that we can recognize assembly language as these mnemonic pieces of code and also understand that assembly language falls into the category of a low-level language. So low-level languages include machine code, which we've discussed, and also assembly language, which looks like this that you can see here. Although it's more easy to understand than machine code, it's still very simple and what we consider as a low-level language. So again, it is important that we recognize this type of code, that we can label it as assembly language, and again, put it in the category of a low-level language. Now, if we look at high-level languages, you might clearly recognize some of this from lines of code that you've written in school, in your own time, but certainly much easier to understand than the previous examples that we've just had. These 3 lines of code have got many words that we recognize from English: if, answer, true, all words that we can easily read as a human, hence why we'd label this as a high-level language. So this piece of Python code that you can see here falls into this category, as would any lines of code from a C++ program, from a Visual Basic program, or any modern programming language that is used in today's world. They would all be considered as high-level languages. Now, as we previously mentioned, assembly code is directly translated into machine code, which meant it was very easy for this translation to take place. Now, with high-level languages, they are a lot more complex than assembly code, which means that when it's translated into zeros and ones, the whole process can be a lot more tricky, but is obviously doable with the processing power of modern CPUs and the knowledge of modern day programmers. But as we move forward in this lesson, we will see how this translation takes place, as there are different techniques that we need to understand and show awareness of for our syllabus. And what these 2 approaches are called is compilation or interpretation. So you might have heard of the words compiler or interpreter, but these are the 2 ways in which high-level languages are translated into machine code so that the computer can execute the lines of code that we write as programmers and we are able to run our programs. So the first method, compilation, or what we call a compiler, is the technique in which our high-level languages are translated into machine code using a compilation process where an executable file is produced at the end. So an executable file just means a file that can be run on a computer without needing to see the lines of code or without needing any other programs in order to run it. So for example, downloading an app off the App Store, you download an executable file and it's able to run without any other tools needed. It simply downloads, installs, and you can use it there and then. So this app or this program will have been compiled when it was put onto the App Store. The machine code that's created by a compiler is also known as object code, if you ever see this term. But object code is just another word for the machine code created by a compiler within the executable file that's produced at the end. During the compilation of the program, if any problems are found or there's a syntax error within your code, what will happen is that an error report will be produced and the programmer will be made aware of these errors so that they can go back and fix them in order for the compilation to be successful. So it's important that when code is compiled, it needs to be completely error-free in order for the successful executable file to be produced at the end. So keywords with the compiler are executable file, an error report if any syntax errors are found, and also object code, which is just another word for the machine code after compilation has taken place. So a way you can think of it, if you think of any app that's available on an iPhone and an Android device, the programs would have been compiled for each operating system before they were released onto the App Store for each one. But as you can imagine, the CPUs and operating systems are different on these devices, so that different executable files will have been produced by the programmer for these different devices and for them to be installed and run. The same would apply with macOS and Windows, or even an Xbox and a PlayStation. The games will be compiled for the specific operating system and hardware in each console. Now, when it comes to an interpreter takes our high-level language and translates it line by line. So it translates each line of high-level language into machine code one line at a time. So the key term with an interpreter is line by line. In the image here, I've got what you call an interpreter, and if the guy on the left is speaking in English, but he's speaking to a Spanish audience, the guy on the right is the interpreter, and after the guy on the left finishes a line or a sentence, the interpreter will repeat that line in Spanish so the audience can understand. But what's important is that he is translating it line by line, not at the end after the guy on the left has finished speaking, because otherwise that would be quite impossible. So it goes through the code line by line, and in this case, if a syntax error is found, it will stop the program, display an error message, and alert the user, telling them where the error might be or what the error might consist of. So with an interpreter, no executable file is produced like it is with a compiler, and the key term here is that the translation takes place after each line of code is written. The last technique is what we call an assembler, and this only applies to the translation of assembly code into machine language. And like we've mentioned, it's the most easiest way, and it's much simpler than translating any high-level language into the machine code that the computer needs. We've mentioned previously that assembly language is directly transferable into machine code, so the job of an assembler is much easier than a compiler or an interpreter. So there's a summary of all three. If you want to pause the video, take some notes, go ahead. But just before we finish off, the pros and cons of compilers and interpreters is that an interpreter is the one that reads line by line, which means it's easier and quicker to debug and test programs during development. If you can imagine writing your lines of code, you run it to see if it works, the program halts, tells you that there's a problem in line 37, you go ahead and fix it, you run it again and test that it works. So it's much easier to debug and test your programs, as with a compiler, you'd need to compile the whole program, see what's in the error report, and that whole process would have to take place every time you wanted to test it. So even if you make one change to a line of code in a program that has thousands of lines, you'd have to compile the whole thing just to see if that one line of code has changed each time you want to test it. So testing and debugging programs is much easier with an interpreter. However, with an interpreter, you cannot run a program without the interpreter being installed on that local machine. So the perfect example that I give for an interpreter is when you write a program in Python, you need Python installed in order to run that program. You create your program in school, you send your lines of code to a friend in your class. Your friend cannot run those lines of code without having Python installed on their machine. So it's absolutely crucial that you need an interpreter in order to run the code. Not only that, programs can take longer to execute as the lines of code are read line by line. So just a reminder on that. With the compiler, once a program is compiled and it's finished, it's stored and ready for use. It can be distributed on the internet, it can be put on the App Store, but it's there, it's ready to go, and it should work. Also, a compiled program does not need the compiler in order to run. For example, the App Store that I mentioned earlier, you download a program from the App Store and it runs without any extra programs needed. A compiled program also takes up less space in RAM when it's executed, and it's also executed in a shorter time than an interpreted language. So those are the key differences between a compiler and an interpreter. And I hope I've managed to explain the differences using those real-world examples. But if you're not familiar with programming just yet, or you're fairly new to it, just hang in there, because once you start, this will make perfect sense and you should be set up for Unit 4 in your exam. So just to finish off, I'd like you to match the type of code with the example. And as you can see, it's fairly simple. We've got machine code on the left here, as we know is the binary numbers for the computer. So that'll be that one there. Assembly code uses the mnemonics, like we mentioned earlier, and that will be this one here. And then a high-level language uses words that we're familiar with as humans, and that goes over there on the left. So as always, guys, I hope that's made sense. If not, drop me a question in the comments below. And don't forget to like and subscribe for the remainder of the course, as we are nearly halfway through and making fantastic progress through our iGCSE syllabus. Thank you for watching, and I'll see you in the next lesson.